I am Golok Chandra Sarkar, Associate Professor of Chemistry, Rajaputtana Model College. My dear students, I hope you all are fine in this pandemic situation and you are following the necessary health rules. Today I shall deliver my third lecture on the chapter Periodic Properties and Chemical Bonding. Our point of discussion today are: number 1, D block elements and transition elements. Then we shall discuss magnetic property of transition elements, melting point of transition elements, and properties of transition elements. Among the properties of transition elements, today we shall discuss transition elements show variable valency, transition elements possess catalytic properties, transition elements form colored compounds, transition elements form complex compounds. Let us start with the definition of d block elements. The elements whose last electron enters into d orbital are known as d block elements. I have given 3 examples here. Look at the electronic configuration of scandium. The last electron has entered into 3d orbital. In copper, the last electron has also entered into 3d orbital, and zinc, the last electron has entered into 3d orbital. So all these elements mentioned in this slide are d block elements. In general, group 3 to group 12 elements are all d block elements. Now let us discuss the magnetic property of d block elements. Actually, magnetic property depends on whether an atom or element contains unpaired electron or not. If a d block element contains unpaired electron, then it is attracted by magnetic field and we say it has magnetic property. But if an element does not have any unpaired electron, then it is repulsed by the magnetic field. If a d block element contains less number of unpaired electron, then it is attracted weakly by the magnetic field and they are known as paramagnetic element. If you write the electronic configuration of scandium and titanium, you will get less number of unpaired electron. Scandium contains 1 unpaired electron and titanium contains 2 unpaired electron. They are weakly attracted by magnetic field and so they are known as paramagnetic element. The elements which have more number of unpaired electrons are known as ferromagnetic elements. Examples are iron, cobalt, nickel, etc. Again, zinc has no unpaired electron at all. All the electrons are in paired form, so it is repulsed by the magnetic field and so the zinc is a diamagnetic element. This is about the magnetic property of d block elements. Now we shall discuss the melting point of the elements of 3D series. The first element of 3D series is scandium and the last one is zinc. You look at the melting point of the elements at first increases with the increase of atomic number. It is increasing up to vanadium and chromium. After chromium it has fall down in manganese, because in manganese there are 5 unpaired electron which gives a stable electronic configuration. Due to this stable electronic configuration, the participation of the valence electron in the metallic bond is less. For this reason, the metallic bond is comparatively weaker and the melting point of manganese is slower than the others. Again, from manganese, the next element iron, cobalt, nickel, etc. The number of electron in the outermost energy level increases and the metallic bonds become gradually stronger. But in copper and zinc, there are 3D electronic configuration which is very stable electronic configuration. For this reason, the melting point of copper and zinc is less than the other elements. These are the changes of melting point of the elements of 3D series. Now we shall discuss about transition elements. What are transition elements? Those d block elements which have incomplete d orbital, that is those d block elements having d1 to d9 configuration in the stable ionic state are called transition elements. Scandium possesses 2 into 1 electrons and the last electron enters into 3d orbital. It's a d block element, but the stable ion of scandium 3 plus, contains no electron in the d orbital, that is the d orbital is totally vacant, so it is not a transition element, though it's a d block element. Again, the last electron of copper also goes to 3d orbital, and so it's a d block element. And the stable ionic state of copper is copper 2 plus, which contains 3d9 configuration, that is the d orbital is partially fulfilled by electron, so it is a transition element also. So copper is a d block element as well as a transition element. What about zinc? Zinc is a d block element, the last electron entering into 3d orbital, and the stable ionic state of Zn2 zinc is Zn2 plus, which contains 10 electrons in the d orbital, that is the d orbital is fulfilled. So zinc is a d block element but not a transition element according to the definition of transition elements. Now we shall discuss the properties of transition elements. Number 1, variable valency, then catalytic property, then colored compound formation, and finally we shall discuss complex compound formation. Now let us start with variable valency. Transition elements show variable valency because the energy between the outermost energy level and the penultimate energy level, here ns is the outermost energy level and n minus 1 d, it is the penultimate energy level. The energy difference between these two energy levels are very little. For this reason, after losing electron from ns orbital, d block elements, that is transition elements, can successively lose electron from n minus 1 d orbital. Let us discuss with the example of iron. The outermost energy level contains 2 electrons in 4s orbital. After losing these 2 electrons, it is getting the configuration of Fe2 plus, and the electronic configuration shows that there are 3d6 configuration in the outermost energy level. Since it is very close to half filled electronic configuration, it is losing another electron to produce Fe3 plus, and as a result it is getting half filled stable electronic configuration. So iron can lose electron from 4s orbital as well as from 3d orbital. For this reason, it is showing two variable valencies, iron 2 plus and 3 plus. Other transition elements also can change their valencies by losing electron from 4s orbital first and then successively from 3d orbital. I have given another example of variable valency, manganese. The electronic configuration of manganese shows that it has two electrons in the outermost energy level, 4s orbital. After losing these two orbitals, it has got the electronic configuration like this, 3p6 3d5, and the oxidation number is now 2 plus. It can lose electron from 3d orbital successively and can make ionic state of manganese 3 plus, 4 plus, 5 plus, 6 plus, up to 7 plus. Now it has lost all the electrons from the d orbital, so it is the most stable ionic configuration like an inert gas. So it is the maximum oxidation number of manganese. So manganese can form 6 stable ions by losing electron from 4s and 3d successively. So it is very clear that transition elements can form variable valencies. They can show variable valencies. Now our next point of discussion is that Catalytic property of transition elements. Transition elements are widely used as catalysts in chemical reactions. How they act as catalyst, we shall understand. We shall try to understand the mechanism first. Let us have an example of the reaction of ethene with hydrogen. Practically, when transition metals like nickel is used as catalyst, the vacant d orbital can attract the electron from the bond electron. Like in ethene, the pi electron is attracted by the vacant d orbital of nickel. As a result, the bond has become weaker since some of the electron density has been absorbed by the vacant d orbital of nickel. Since the bond has been weaker, the bond breaking process has become easy. It takes less energy to break the bond, and the reaction uh, occurs very fast. So nickel, by making the bond weaker by absorbing electron, it is accelerating the rate of the reaction between ethene and hydrogen. So by using the vacant d orbital in transition element, they can act as catalyst. Now we shall discuss another very important point. Transition elements can form colored compound. How they can form colored compound? Before understanding that, we have to know some terms. Uh, Actually, the orbitals of the same sublabel have same energy. Look at this. Uh, 3d orbital of iron containing 6 electrons, and all the 3d orbitals have same amount of energy, and this state of orbital is called degenerate state. Degenerate state, when it forms compounds and it absorbs required number of uh, ligands like water. The d orbitals are splitted into two groups. The 5 d orbitals are splitted into two groups. Two orbitals will get higher energy and three orbitals will get lower energy. As a result, the 5 degenerate d orbitals will be divided into two groups, EG and T2G. T2G. When light falls on this type of compound, electron from lower energy orbital will absorb the fraction of light from the visible light, and will jump to the higher energy level. Since in visible light there are seven colors, we know. In visible light there are seven colors, we know. By absorbing a fraction of this light, electron jumps from lower energy orbital to higher energy orbital, which is called dd transition. Because of dd transition, a fraction of visible light is absorbed and the remaining part is reflected to our light. Since the fraction of visible light has been absorbed during the dd transition, the reflected light uh, will be a colorful light, because we know visible light is a combination of seven colors. If some fraction of this um, color is absorbed during dd transition, the reflected part will be a colorful one. So uh, transition elements actually form colored compounds because of the dd transition, because of their dd transition. Now we shall discuss another very important property of transition elements: complex compound formation. What are complex compound? The compound which contains complex ion. Actually, complex ions are formed by the metals of d block elements and transition elements by forming coordination bond with some uh, neutral molecule or ion. Let us discuss the point with the example of iron. Look at the electronic configuration of iron 2 plus. Iron 2 plus has a total of 24 electrons actually, and when it forms complex ion with the ligand cyanide ion. Uh, it gets 6 into 2, 12 electrons from 6 cyanide radicals. As a result, the total number of electrons becomes 24 plus 2 into 6. I repeat, uh, iron 2 plus has a total of 24 electrons. Uh, it has 12 electrons short from the electronic configuration of the nearest inert gas krypton. From the nearest inert gas krypton. For attaining the electronic configuration of the nearest inert gas krypton, it manages 12 electrons from 6 cyanide radicals by forming coordination bonds, because every cyanide radical can provide one lone pair, that is 2 electrons. So it needs 6 electrons to cover up the shortage of electron and to make the total number of electron 36. So 6 cyanide radicals are forming coordination bond with the central metal ion, and a new ion is formed which is called complex ion, and the name of this new ion, which is charged -6, is ferrocyanide ion. The charge is calculated by the summation of the charge of the central metal ion with the charge of the negative radical or neutral molecule with which the central metal ion is forming coordination bond. In this way, transition elements form coordination bond with neutral molecule or negative radical to form a new type of ion which is called complex ion, and the compound which contains this type of complex ion are known as complex compound. Transition elements can form this type of compounds only. Now, what are ligand? In the complex compound formation, the negative radical or neutral molecule with lone pair electron which form coordination bond to produce complex ion is called ligand. Look at this, the neutral molecule, in this case it is ammonia, neutral molecule or negative radical, in this case it is cyanide, which form coordination bond, which is indicated by arrow sign, which form coordination bond with the central metal ion, are known as ligand. So in ammonia is a ligand as well as ammonia is a ligand as well as cyanide is also a ligand. Ammonia is a ligand and cyanide is also a ligand. I repeat the definition. Look at this, the negative radical, here the cyanide radical, or neutral molecule, here the ammonia molecule with lone pair electron, both of them have lone pair electron which form coordination bond. They both are forming coordination bond. Coordination bond to produce complex ion is called ligand. Now another term, coordination number. What is coordination number? Number of coordination bonds formed by the ligands with the central metal ion in a complex ion are known as coordination number. I repeat, number of coordination bonds formed by the ligands with the central metal ion in a complex ion are known as coordination number. In ferrocyanide ion, coordination number of iron is 6 because 6 cyanide radicals have formed 6 coordination bond with the metal ion iron 2 plus. So the coordination number of iron is 6. Again, zinc has formed 4 coordination bonds with the ligands ammonia. So the coordination number of zinc is 4. So we have discussed some properties of transition elements here. I think you have got clear idea about the properties of transition elements. Now I have given you some question for homework. Solve this problem by yourself following this video lecture. You can also take help from your books also. Thank you very much for enjoying this video lecture. Thank you all. Take care.